Okay, everyone, thank you for joining me here this afternoon to go over continuing webinar series here that SES America has. Today, we're going to talk about solar-powered ITS devices, some of the design and that goes into some of these solar power systems, and some of SESA's technology that's well suited for solar applications. My name is Brandon Tessier. I am the Regional Sales and Account Manager for SES America. I've been with SESA for about 3 years. We've been really digging into solar technology for 3 or 4 years now. Our company is dedicated to ITS and dedicated to the transportation industry. All of the products that we manufacture and engineer are strictly for transportation. The company just celebrated its 30-year anniversary, and we distribute our products across the U.S. and in Canada. We really try to focus on innovative technology, customized solutions, and customer service. And you'll learn a little bit about that innovative technology here today and how it pertains to solar power and our energy efficiency that really is well suited for these solar power systems. We are certified ISO and NEMA. All of our components meet all NEMA certifications. Most of our communication is done via NTCIP, especially for our dynamic message signs. We do have blank out signs that use simpler communication methods, but for any of our intelligent equipment, all of our communication is done via NTCIP. As I had mentioned, we really focus on customer service. Every project that we do, we have a dedicated technician that is available 24/7, 365. All of our clients have access to their dedicated technician directly through their cell phone and email. So it's something that we really try to focus on. And off-the-shelf solutions, certainly something that we do, but customized solutions is something that we really focus on as well. So we're able to develop, engineer, and manufacture signs of a lot of different sizes, whether it be dynamic message signs, blank out signs with unique graphics. Customized solutions is something that we really excel at as well. All that has led to some nice awards for SESA over the past few years. Last year we won an award for Best Manufacturing, Overall Excellence in Manufacturing. Just this year we were awarded the Best Place to Work in Rhode Island. And in 2014, we won an award for our solar power design. It was the ITS Product of the Year. So we've done our due diligence on solar technology and our solar products, and I'm looking forward to sharing some of that with you guys here today. I'm going to talk briefly about how solar has become more popular and deployed more and more over the past decade, and some common myths that we encountered when we first started looking at how we could provide some of our equipment with a solar power system application. Talk about why these systems are feasible, the economics behind them, the size of the solar power systems, and how technology has allowed these systems to become feasible. And then reliability. I think any solar power system, it's great if it's affordable, but it has to be reliable. We want to know that these systems are going to be working around the clock. So we'll talk about how we design our systems to be reliable. And then we'll get into our technology, SESA's technology, and how it relates to solar and our solar-powered DMS, and show you guys a couple of case studies. Like I mentioned, the Q&A can be done anytime throughout this, so just hit me up with a question through your control panel, and I'll try to answer it as we go through the presentation, and I'll also open it up to some questions at the end. So just in general, the use of solar power systems, we've seen a big boom over the past decade with an annual growth rate of nearly 60%. I think that that's probably not a huge surprise to most people here attending this, as we've seen green initiatives really become more and more popular and more mainstream over the last 10 years. And when you combine that with the reduction in the cost of what these solar systems carry, that really has led to more and more markets across the nation deploying these systems. That includes residential, where right now there's solar installations that generate enough electricity to power over 6 million homes, but also commercial, where we've seen corporate America look at corporate look at solar installations across the U.S. Right now, 38 states that have corporations with active solar power systems to power anything from distribution centers to retail stores to offices and manufacturing centers. And the map that you see on your screen now kind of shows how that is spread out across the country and the different types of facilities that corporate America is using solar power to provide the energy that they need to power those facilities. Besides corporate America, we're also seeing cities and towns start to really try to go green and use renewable energy. Over 10 cities have already committed to being 100% powered by renewable energy in the next 20 years. That's not strictly solar power, but solar power certainly plays a big part into that. And it's not just out west or in the Midwest, it's really spread. You see some of these locations in the Northeast, as well as across the Midwest, and then quite a few out in California. So with all of these different entities taking on solar power, you know, we look at how do we bring more solar power to the ITS world. I think there's a great untapped opportunity in the transportation industry to have solar power brought to all of our ITS devices. If it's not just dynamic message signs, it's cameras, it's Bluetooth readers, other detection equipment that can all be solar powered. One of the things that SESA looked at is if we can have a full-size dynamic message sign that is keeping solar powered, we can power almost any ITS device. Dynamic message signs are going to consume far more energy than any other ITS device. So having solar power systems that can operate these large dynamic message signs really opens up a lot more opportunity for us. Some of the advantages to doing this, and you know, why do we want to have solar power installations? We're going to reduce the amount of civil works that we need to have to set up systems that are powered from the grid. Trenching and running conduit and power cabling to be able to hook up to the grid is costly and it's expensive, and it takes a lot of time. So we get to reduce our installation time, effort, and expense by eliminating the need to do that. We're also going to reduce some of our maintenance costs. These solar power systems generally have less components than AC powered systems, and so we have less spare parts to maintain, and we lower our maintenance costs overall. Of course, as long as the sun is around, the energy is free. So we can eliminate our recurring energy costs. We're getting our power from the sun. So once these the solar arrays and solar power systems are in place, we no longer have to worry about paying for energy costs. One of the other advantages is emergency management. Oftentimes, when in the ITS world, when we need our equipment the most, when we need our cameras, when we need our dynamic message signs to send out advisories, it's times when there's been a natural disaster or we have weather that's moving into the region. And just as part of that, we can lose power. And with solar power systems, we're able to still get that messaging out. We're able to still use our cameras and our other ITS equipment without having to rely on power from the grid. And then one of the last advantages here is a green footprint. You know, just using renewable energy is better for our planet as a whole, and is a better way to go when we're taking a look at our power options. So I want to talk about some common myths. These are some of the things that we have run into as we started to look at deploying solar power. What have different customers or different DOTs come to us and said their concerns are about solar power, and especially as solar power relates to dynamic message signs. And one of those is that solar power DMS won't operate 24/7. All of these solar power systems are designed to have battery banks so that even when we don't have sunlight, the batteries are able to operate the dynamic message signs and controllers without needing any sun. There's autonomy that is built into each of these systems so that if the solar power system is completely disconnected from the photovoltaic array that's capturing sunlight, this equipment will still be able to operate, and for days on end, based on whatever autonomy you set. So these systems certainly can operate 24/7. Solar powered DMS are limited in size. The only thing that we have to consider when we consider the size of our DMS is the size of the associated solar power system that'll go with it. Anything in the world can be powered by solar energy. It's just the amount of the size of the solar chain that you're going to put in place. Obviously, we don't want to have a system where we have 500 solar panels and 1,500 batteries. That may not be that feasible. But for solar powered DMS, even though they may consume a lot of energy, we find that if we use the right type of components and we design the DMS properly, the solar power systems, we can have smaller solar powered systems that are able to power almost any size dynamic message sign. Regarding the visibility, so solar powered DMS are less visible. And I end up hearing this question quite a lot, you know, as your battery bank is depleted, does the light output from your LEDs also diminish? That's not the way that these systems work. These systems will operate at 100% until the battery bank is completely drained. So even if you only have 5% of your available battery left, you'll still have the full output of power to the sign. You'll still have the same luminosity from your LED displays, and those LED displays will be meeting NEMA optical requirements. So the battery bank, until it's completely depleted, will continue to provide all the power necessary so that these signs are as visible as any AC powered DMS. A solar powered DMS can't be mounted on overhead structures. Any of these DMS, the difference between a solar powered dynamic message sign and a traditional AC powered dynamic message sign is in the components that go inside the sign itself. So the housings are identical, and the mounting apparatus that we have for each of these different signs, whether they be front access or walk-in signs, is the same as they would be solar powered to AC powered. So these can be put on cantilevers, overhead butterfly structures, high masts, I-beams on the side of the road. For arterial DMS, any of these DMS can be mounted just as you would mount any other DMS. Solar powered DMS require too much maintenance. The solar panels themselves are coated with a substance that is designed to have snow run off of the solar panel. These panels are also tilted so that snow and other material will roll off of them, and just a simple amount of rain that comes through will help wash the panels and remove any debris. So there really is no more maintenance that needs to be done for a solar powered dynamic message sign. And in fact, what we'll get into a little bit later, you'll see is with less components in a solar powered system, we're actually going to reduce the amount of maintenance that we have to do for a solar powered DMS. Then there's always the question of cost. Are solar powered DMS too expensive? Well, there's going to be a small uptick in cost in the beginning. You're not just hooking it up to the grid. You do need to install a solar power system, and the components themselves carry a bit of an additional cost, but it's negligible, and that cost is quickly recuperated. Our calculations show a return on investment in only about 4 to 5 years. So I did get a question here about battery maintenance. So we'll get into battery maintenance here in just a bit. So we'll give it a few minutes here, and I'm going to get into what we use to maintain batteries and how we try to optimize our battery banks to make sure that they're going to last for as long as possible. Okay, continuing on here. Myth number 7, solar powered DMS technology is not reliable. Well, we're going to get into system design. I think that anytime you look at solar power systems that aren't reliable, it's because they're not properly designed. And as we got brought in to look at other ITS devices that were powered by solar, we found, for systems that weren't reliable, we found that there was deficiencies in the designs of those systems. And we're going to spend a brief portion of this webinar going over system design and how you need to design these systems so that they are reliable. If you do so, that these solar-powered dynamic message signs are in fact very reliable. So getting into solar power feasibility, I think that before we get into the design portion of this, which will come next, these solar power systems have to be feasible. The solar systems themselves can't be too large. We may not have the available real estate, especially on roadside conditions, to be able to install solar power systems, dynamic message signs, or any other ITS device. So the solar power systems themselves have to be smaller in size, and there has to be a certain economical advantage to being able to install these. If price becomes prohibitive, then the system itself is not very feasible. Overall, these solar power systems, in fact, are cost-saving solutions. We've seen a decrease in the cost of solar components, and if we use efficient components in all of our ITS devices, then we don't need very large solar power systems. We're going to reduce the cost of civil works, installation time and effort, maintenance, and we're going to eliminate recurring energy costs, which I touched on before. So overall, when it comes to the cost of these systems, that is not something that we have to be too concerned with. These solar systems have become more and more affordable over the years as technology gets better. Here, this graph shows just the cost of PV panels, which are, of course, a big part of the system. Just from 2011, we were at about $1.35 a watt for these PV panels, and as of this year, that cost has dropped down to about 65 cents a watt for these PV panels. So just in the last 5 years, we've seen the cost of the PV panels alone be reduced in half. And that has to do with technology getting better, efficiency getting better on these panels. We now can use smaller panels that are capable of capturing that solar radiation much better and converting it into energy. Some of the other ways that we can save money by using solar-powered ITS and solar-powered dynamic message signs is in the installation, that the money that we're going to save during installation. These graphs here show what the cost analysis is for a traditional dynamic message sign versus a solar-powered dynamic message sign. So you see the difference here in the cost of the DMS itself. The solar-powered DMS that uses more efficient components does carry an upfront cost. And now we've also factored in costs for the solar-powered DMS of the PV array, the battery bank with some of the control equipment that needs to be included with that. Communication, we're going to want to include a cellular modem here so that we don't have to do trenching to run communication cabling or anything like that. So this is included, and cellular service that has to go with that cellular modem. Then on the solar powered DMS, we've also included a battery bank replacement, which kind of gets into the question one of you had asked just a few minutes ago regarding maintenance. No matter what we do for our solar power systems, batteries are only going to last so long. We can maximize the length of the battery life by proper design and by taking care of these batteries. But they're not going to last forever. And with a dynamic message sign that has a lifespan of 12 to 15 years, you're going to see that you need to replace the battery banks probably once midway through that lifetime. So I have another question here that comes about the battery life, and yeah, I maybe just answered that a little bit. We've reached out to different battery manufacturers to find out what they can really give us for a firm number on what expected battery life is. And the answer that they've all come back kind of universally to us with is that the battery life is really dependent on how the system is sized and the design of the system overall. Improperly designed systems are going to really shorten the life of your battery bank, the way that these batteries are stored, the cycling of the batteries. It all really plays into the battery life. Properly designed systems, the feedback we've gotten from battery manufacturers is that when they're properly sized, they might last on average between 5 and 7 years. Most of them will warranty them for about 3 years, but that is with a fully vetted system design. So they want to see the system design that is in place and make sure that it has been sized properly. And I'm going to get into some detail about that battery bank design here in just a few minutes. The other component here to the solar powered DMS is the cabinet to store the batteries themselves. So total cost just under $79,000. Now you take a look at that compared to traditional DMS. And once we factor in the civil works, there's kind of two different charts here, one for civil work of 1/4 of a mile and one for civil work for 1/2 a mile, trenching, conduit, pulling cabling. When you combine that civil work cost with the recurring energy costs of these dynamic message signs, you can see that the cost is double to triple, almost triple what it is for a solar power DMS over the lifetime of the sign. Some of that installation cost analysis, when we talk about civil works, just so everyone can see kind of how that is calculated. There's pull boxes and junction boxes. For every 50 or 100 feet, you typically need a pull box or a junction box. There's the installation of those boxes, cabling, conduit, typical trenching, and don't forget that trenching costs can vary greatly by soil conditions. So if you're trying to drill through rock, it's going to be quite a bit more than $5 a foot. And then you have your electrician labor that you have to factor in as well for anything that you're doing when you're trying to hook up any ITS device, including dynamic message signs, to the grid. So total cost per 100 feet, just over $4,000, and that has to be factored into our cost, and that was factored into the slide I showed before. Recurring energy costs, so this just shows a 28 by 125, which is about 3 lines of 15 characters for an amber LED DMS full matrix. Shows the power draw. This is based on kind of an industry standard for the watt draw per display board. And this does not include any additional energy that you might have, for instance, in a walk-in unit where you have ventilation systems, or if you include heaters and fans to deal with condensation or cold weather temperatures inside the DMS housing. None of that's really factored into any of this energy cost. So just for the LED displays, displaying with about 70% of your pixels for basic messaging in amber, running 250 days a year, you can see your cost is just under $2,000 a year and just under $25,000 a year just in the energy cost for a AC powered DMS. Maintenance would be one other thing that we would want to consider. So AC powered dynamic message signs, we need to convert that power to DC in the sign housing to run all of our components. This is going to be the same for modems or cameras. We eliminate the need to have power supplies when we go on a solar powered system. Everything is provided via the battery bank, which is DC powered system. We also eliminate heaters and fans. We don't install those in solar power signs because all of the components that we use are NEMA rated and can withstand temperature extremes. So we don't need heaters or fans to deal with those temperature extremes. And we're also going to deal with limited spare parts inventory. Like I mentioned, no power supplies, a few other components that aren't needed in solar power DMS. That's going to lower our spare parts inventory. We're going to have fewer points of failure in these signs, and we're going to have less to deal with maintenance. Okay, so let's get into the design, because this is really where, if you want to have a reliable solar power system, this is kind of the meat and potatoes of everything here. We have to design the system properly. We'll talk about energy efficiency here, and we'll get into how SESA's dynamic message signs deal with some of that and are well suited for these applications. So when we look at the solar chain calculation, we have to get a critical design analysis that's going to take a look at the amount of power that the components are going to consume and the amount of power that we're going to be able to capture from the sun using our solar power system. We need to calculate that carefully and correctly in order to really have what we call critical design analysis. Part of that, as I mentioned, is the load analysis. We need to see how much power our components are drawing. Desired autonomy, how much power do we want to be able to have in reserve in the battery bank to be able to power these systems when we don't have access to the sun, or if the system should become disconnected from the PV array, et cetera, et cetera. Take a look at the battery bank configuration, how many batteries we're going to need in order to achieve that autonomy. In the PV array configuration, how many solar panels do we need, given our location, to be able to capture the right amount of sunlight and properly recharge these batteries every day. That critical design analysis, really, it's all hinges on planning for the worst. We want to figure out a higher amount of energy consumption, a higher amount of that load. We don't want to take really safe estimates and then find out that our system is consuming more power than we thought, and now we have an undersized system. We also have to not count on too much sunlight. We can't design this entire system based on the amount of sunlight that's available in July. Otherwise, when we get into December and that available amount of sunlight is cut down in half or a third, now all of a sudden we have an undersized system again, as we're not able to capture enough sunlight every day to start to recharge our battery bank. Part of that critical design analysis is coming up with a critical design ratio, which is what I just spoke of here. What is the load? How do we properly calculate load? And what are we going to take a look at for average daily insolation, or what is the amount of sun that we can really reliably have at site during any of this, during any time period based on our location. We want to use this data to size the entire system to really get an accurate picture of our system availability. When doing that load analysis, we want to consider what is the existing load and what might the future loads be. Is the load going to vary based on the time of year? Are we using certain ITS equipment more during the summer based on its location and less during the winter? So how will that change monthly and annually? We need to take a look at that and figure out what the load analysis would be based on those conditions. If we find out that we're using these systems more during the summer, we want to use that load analysis, the amount of power that's consumed at the maximum amount of time to be able to calculate our system. That's how we properly size these systems. Peak power demand, we look at a manufacturer statistics, take a look at your data sheets, figure out what is the max power draw on your modem, on your power supply, or on any of your other components to figure out really what is the peak power based on how many hours I'm going to need to be using it at site. You can also hook up any of these components to an operating voltage meter, figure out your current and your voltage, and get a better idea of your energy consumption. Now, we have to be a bit responsible here. If we go to the absolute extreme and figure on the absolute worst case scenarios, we might end up with a solar power system that is a bit oversized. It'd be better to err with caution on that side here, but as accurate a picture that we can paint with our load analysis will help us really properly size the system so we don't have too many batteries or too many panels. At the same time, we don't have too few. So here's an example of load analysis and how this was kind of done on embedded dynamic message sign that SES America installed for MassDOT here. This was a travel time sign that had 3 display modules, had a DMS controller, had communication done via a modem, and had a Bluetooth reader and a solar charge controller to regulate the power coming from the PV panels to the battery banks. So we took a look at our power rating on the display modules and the controller and figured those to be operating 24 hours a day. But you can see the modem and Bluetooth reader 12 hours a day and 18 hours a day, because a modem doesn't constantly transmit data, especially for these travel times. We were able to talk to the software company processing the travel times, and we were able to figure out how often they would be actually polling the modem. And based on that information, we were able to determine that that modem would actually be operating at peak power for about 12 hours a day. We factored that into our calculation to come up with an accurate number. So this kind of gets back to what I was just saying of, you want to calculate for the worst, but this would have been a bit overkill for us to factor in the modem operating at peak power for 24 hours a day. It would have caused an unnecessary increase in the load analysis that we had here and increase the size of our solar power system unnecessarily. So talk a minute here about autonomy. So one of the things to consider here is how much autonomy do you want to have built in on your system? The amount of autonomy is going to be directly related to your load analysis and the size of your battery bank. So the higher the autonomy that you desire, let's say that you desire 20 days of autonomy, again, meaning that the system, the battery bank is completely disconnected from the solar power array. How long will that run? It would run for 20 days just on battery. That'll be based on your load analysis and how much power you're consuming every day for that particular location. The higher the autonomy that you have, the more costly and expansive your solar chain will be. And also the higher power consumption for your components will increase the size of your solar power system, or if you're only limited to a certain size power system that you're able to install, it'll lessen your autonomy. So we want to try to use energy efficient components, get a good idea of what our load analysis is, and then figure out what might be an acceptable autonomy. Or conversely, you can figure out what you want your autonomy to be and take a look at your load analysis and then figure out what you need to have for a battery bank. The battery bank is sized strictly on the based on the autonomy that you're desiring to have. So this has nothing to do with the PV panels or any other part of the system. Autonomy is strictly related to the amount of power being consumed and the amount of days you want the system to be able to provide that power without having any connectivity to any sunlight. That will tell you how many batteries you're going to need in your system. So the battery bank itself, of course, this is the heart and soul of the system. This is what's going to provide power to our entire system during periods of low sunlight or low insolation, and also be able to store some of that excess energy during periods of high insolation. The system itself, the battery bank, will determine the DC voltage. So if you have a system that you're wanting to run off of 24 volts DC, you need to have a battery bank that's going to be operating at 24 volts DC. The capacity, as I just mentioned, is dependent strictly on the load requirements, how much power we're consuming, and the desired autonomy that we have. We're going to get a little bit more efficiency the higher voltage systems that we use. So if you can get up to a 48 volt system, it's going to have a little bit less current, and it's going to provide a little bit more efficiency. The type of batteries that we use for solar applications are typically AGM. We also have gel lead acid. Flooded batteries are part of this, but being phased out because we go more to absorbent glass mat and gel lead acid batteries. These batteries are able to withstand greater temperature extremes, and they're meant to be cycled constantly. With any battery that we have as part of a solar power system, to really extend the life of the battery, we want to be constantly cycling these batteries. That means at night we want the components to be drawing power from the batteries and drawing them down, and then we want to get sunlight onto the PV panels during the day, providing power back to the batteries and charging them up again. This type of constant cycling is going to increase the battery life. It's something that the batteries need. If they're just left to sit idle, they're going to slowly drain, and it's going to hurt the overall performance of the batteries. One of the other things that will affect the performance of the battery is temperature extremes. The batteries are going to put out less power based on the colder the temperature gets. This is something that we need to really factor in as part of the losses when we size our system. If a location that you're going to be installing this has lows that might drop to around freezing, you need to factor that in. Typically, battery output is only going to be 80 to 85% of peak once the temperature drops down to around freezing. Every battery manufacturer has a chart that they provide on a data sheet that shows the derating based on the different temperatures. You want to factor that in when you're doing your system design. You need to take a look at what you anticipate the low temperatures to be, and then apply that derating factor to your battery bank and apply that for a year-round calculation. So if it's 0 degrees and the battery is only going to operate at 80% output, you want to use that 80% output number of the battery bank for the entire system and figure how many batteries you need to have based on that. One of the ways that we can protect batteries from both cold and heat is by insulating the battery cabinet. In the photo that you see here, this is from an actual installation. This is a fiberglass insulated battery cabinet. It's painted white. So we're really trying to deal with temperature here in a few different ways. First of all, the material, by using fiberglass, it's less of a conductor of heat. We're powder coating that with white to help with reduce some of the radiation that's picked up by the cabinet, and then we're insulating the cabinet as well to protect it. Batteries will perform with less output during colder temperatures, but they'll recover from that. You can bring a battery down to freezing, and then once it gets warmer, that battery will just start resuming operating at full capacity again. But it's not true for heat. As batteries get exposed to temperatures that are higher than they are rated for, they can be permanently damaged. So while they'll recover from the cold, if you expose your batteries to too much heat, you will damage the battery. And if it's exposed to too much heat, it'll be permanently damaged and it'll have to be replaced. So protecting these batteries is something that is very important. One other item here is the depth of discharge. As we look at calculating these systems, if we figure in the amount of batteries that we need to provide power to the system, we have to consider at what amount of discharge are we willing to let our batteries get to provide that power. So if we want 10 days of autonomy, and we know that that is going to require a battery bank that requires 10 batteries, is that 10 days of autonomy going to be provided by drawing the batteries all the way down to almost no power? The battery life is going to be correlated with how much drawdown we give those batteries. An optimal system will be sized to provide the desired autonomy that we have while only drawing the battery down to about 50% of its overall power. So this chart kind of shows that here we're going to double our battery life if we go from drawing down the batteries 80% to only drawing them down 50%. Now, if we draw them down 10%, obviously you see here there's a big jump in the amount of life expectancy for the batteries. The problem with that is you've now created a solar power system that's going to have an enormous battery bank. You need much more batteries if you're only counting on drawing the overall battery bank down 10% at any one time. So the 50% number is a good middle number to have. Size your battery bank so that at any time you're only drawing it down about 50% and still maintaining the autonomy that you need. Talk about the photovoltaic panels here. One of the other big parts, obviously, of the system. Most of the panels that are in use today are crystalline silicone. These are the best cost to performance PV panels that we have out on the market. There are other technologies available, but they can be very expensive. So most of them that we see are crystalline silicone. We have to be able to size this PV array to be able to recharge those batteries based on the amount of sunlight that we're going to be able to get at any particular location, accounting for some normal system losses like soiling of the battery, soiling of the PV panels, and some temperature losses that will affect, some temperature that will affect the PV output. Here we take a look at solar insolation as being one of the biggest factors when sizing our PV array. We have to, again, as I mentioned, not calculate the system based on the amount of sunlight available in July, when it's going to be much higher than it is at other times of the year, but rather for the worst month. By figuring out the lowest amount of solar insolation we have at any one given month at a particular site, we can really help get back to that critical design ratio, which is taking into factor the proper amount of load analysis based on the amount of sunlight that we also have. I have one other question here. It says colder ambient temperature allows for better solar panel performance, correct? Yes, as these panels get colder, it's the opposite of batteries. As the temperatures drop, the solar panels will actually provide a higher output of voltage. So yes, that is correct. PV panel tilt, we want to make sure that these panels are tilted to the correct orientation. Typically, if you're looking for what is best just year-round without having to go and adjust those, it's just tilt the panels to the latitude at site. And then we can adjust that based on the summer and the winter. We need to factor in some losses too. For instance, a 300-watt PV panel, it's going to perform differently at different temperatures. So what are going to be the temperature extremes that we're going to see here for these PV panels? Again, it's just kind of the opposite of batteries. How warm is it going to get? Because the warmer it gets, we're going to have a little bit less in performance of the PV panel. Also some soiling derating. These are used in outdoor applications, and for this, what we're talking about here, ITS devices. We're looking at roadside conditions where you can get salt from the roads or whatever else, dirt that is going to accumulate on the PV panels. Once the next rain comes, it washes most of that away, but you do want to factor in a soiling derating factor. Typical industry standard for that is about 10%. So you lose about 10% of the efficiency in your panel at any one given time based on some of the soiling. If you factor that in now, you don't get yourself into a position where you think that your panel is putting out 300 watts when it's actually 10% less because it has some soiling or the temperatures are higher. This graph here kind of shows some solar insolation data and what it looks like, available peaks insolation at any different location across the country. And then this chart shows how that can vary just based on, this is, I believe, for Boston, Massachusetts, and what the peak insolation is, the peak sun hours that we're getting per day. So you can see here, if you sized your system in July, you're getting over 6 hours of peak sunlight. You might think you only need a couple of panels to be able to fully recharge your battery bank. But once it comes to January, you're down to 2.7 hours. That's been cut by over 50%. And now those PV panels aren't getting nearly as much sun on them. They're not able to recharge that battery bank. And now we get into undesirable depths of discharge, where your batteries are going to be constantly discharged below 50% and may even reach a point where they could fail. So we want to use the lowest amount of insulation that we have, and then go ahead and use that to size our entire system, figure out how many PV panels that we need based on that data. Variable tilting and variable load, so you can see here what your different design ratios might look like based on the different months of the year and how tilting your panels would have a different effect on that. We can tilt them by 15 degrees plus or minus in the summer or winter to try to better capture the arc of the sun as it goes over the horizon based on those different times of year. One of the last points I want to mention regarding design is solar shading and how that has an effect on all of this. We go out, you want to be able to do a site analysis at any one of these locations, see how much shade you're getting cast from nearby objects and how that's going to affect your solar panels. And that really is due to the design of the solar panel itself. Solar panels, if they get, as you can see here in panel A, even just one solar cell that is shaded, there is a bypass diode at the top of that solar cell that will disconnect all of those cells that you see in the red X's and bypass those two columns. The reason why is solar panel design, that one cell, if it is allowed to be part of the entire current path, it can create a hot spot which will burn out the panel there and could actually cause a fire. So these bypass diodes are designed so that this portion of the entire panel is shut down and the current is able to pass along that through a different path more safely. So by just having shading on one corner of this panel, we activate the bypass diode and we end up losing 50% of that panel. If the same amount of shade is cast along the entire bottom of the panel, both of those bypass diodes are going to activate, and the entire system is just going to say, I'm going to skip this PV panel entirely and just move on to the next one, and now you've lost an entire PV panel. Obviously, if you've designed your system to have these PV panels providing the amount of power that you need to recharge your batteries, and you lose half of a panel or an entire panel, that's going to be very detrimental to your system. So these are really designed to prevent these hot spots and these burnouts, and so we need to factor in shading at any site to be able to eliminate it as much as possible and eliminate activating these bypass diodes and have it impact our panels. The last part of the system is the solar charge controller. The critical part, it's going to actually draw the power from the PV panels. It's going to condition that power and provide a cleaner power to the batteries. It's going to prevent high voltage and low voltage instances and disconnect the system at times of either high voltage or low voltage. It's also going to prevent reverse current, where your batteries have more power than what your solar panels have, especially during the night. What you can see is power flowing from the battery bank back into the PV panels. This solar charge controller is going to prevent that. It's also able to be set So if your batteries reach a certain depth of discharge, it will disconnect the batteries from the system so there's no longer any power draw, and it can send an alert that lets the user know my battery bank has reached this depth of discharge. This is something that you want to come out and address. Okay, trying to wrap things up here, so I know we're getting towards the end of the hour. Let's talk about how SES America's design is especially suited for some of these solar applications. I mean, we've seen how much energy efficiency really ties into all this, and how we need to have a smaller solar power system in order to be able for the solar to be economically feasible and viable. What has SESA done to try to address that? We talked about our design, but really the focus is on our energy efficiency. Any of the solar sign DMS that we do are fully operational, consume very little power, and are NEMA rated for harsh weather conditions. Some great ideas for deployments for these are rural highways, arterial roads, heavily congested areas, travel time in remote locations, evacuation routes, and seasonal traffic, where we may not need to be connected to the grid to have power year-round, whether that be beaches or ski resorts. We can use solar power and solar power DMS, and it's a more efficient installation. To guarantee reliability of these dynamic message signs, we take a look at all the things that I've mentioned. We look at worst case scenario calculations, take a look at regional weather patterns, protecting that battery bank, and using a unique technology. SES America's dynamic message sign for solar applications is not simply our traditional dynamic message signs that are then connected to a solar power system. We use unique components in our solar power DMS to be able to have them optimized for solar power. The components are more efficient. We use a high intensity LED display board. That means we need to draw less power to be able to get the amount of light output that we need for each of these LEDs. On average, those LED display boards are 4 to 5 times more efficient than the display boards used in the rest of the industry. We also use sleeping mode electronics, so all of our components that are used in a solar power application are able to enter a sleeping mode. They draw no power when they're in sleeping mode, so there's no drain on the solar power system when they're not actively being used. One of the other items that we have here is precise brightness control. We provide a greater level of brightness control that is driven to the LEDs than we do in traditional DMS. That enables us to really fine-tune the amount of power that is being sent to the display board at any time, so that we're not having to push too much power and provide a brightness level that, while is sufficient, may be even more than we need given the light conditions at the site. Maximum power point tracking controller, so we use that MPPT charge controller as part of this system as well to really maximize the energy efficiency in the dynamic message signs, monitor our battery banks, and monitor the overall power of the system. This just shows a different graph on the energy efficiency here. The industry standard messenger, which is our traditional dynamic message sign, and then solar messenger or solar sign, which is our dynamic message signs expressly designed for use in solar power applications. All of these dynamic message signs that we do are built with the same type of housings. We're going to change some of the components on the inside, but they are just like any other standard DMS as far as the display capabilities. 8-inch, 12-inch, 18-inch characters, 1, 2, or 3 lines with a full matrix display, available in front, rear, or walk-in access types with various mounting solutions. And you see the photos here. The one at the top that has the stay alert message is an arterial DMS mounted on 2 posts. And then the one on the main slide is actually a full walk-in with a catwalk that has the solar PV array installed as part of the support structure there. So anything from smaller arterial signs to full walk-in. Again, we use high intensity, low power consumption LEDs. We use the same controller that we use for any of our other DMS, fully NTC IP compliant. It has a full color touch screen, which allows easy diagnostics right from the cabinet without needing to hook up a laptop. And it's available in many different sizes here and configurations. Currently, due to the power consumption, we offer solar-powered dynamic message signs with amber LEDs and with white LEDs. Our Solar Sign 5000, this is just a smaller embedded DMS that we use with solar power applications. The same type of high power LEDs. A little bit more mounting options here. We actually have a unique tilting mechanism which allows these embedded DMS to be angled a little bit more towards the roadway based on different road conditions. If you have curves in the road or winding roadways, we can actually mount the static sign perpendicular to the road and then angle the embedded DMS so that it's better viewable to passengers on these winding roads. Customizable sizes and configurations, we can do these as small as 2-digit travel time to 10 to 15-digit lane status signs, hot lane toll rate signage, and some wayfinding signage that we've done a few projects that have wayfinding and way station status, open close status signage as well. A couple of examples of that. This is the Go Time project that we recently completed in Massachusetts. So we manufactured 350 of those embedded DMS modules for 131 locations across the state that are all being powered by solar energy. Along with the 131 travel time locations like you see on the slide here, we also did an additional 137 locations that had Bluetooth readers to collect Bluetooth data that were also all solar powered. These were all built with 30 days of autonomy. So the battery bank is able to run these locations for 30 days without any connection to the PV array and any sunlight. So that was quite a robust requirement that MassDOT had that we were able to meet. As part of these travel time systems, we also had wireless modems and we had Bluetooth readers, not only at independent sites, but as part of each one of these sites, had its own Bluetooth reader and modem in the same cabinet that the DMS controller was in. Lastly, we did 3 full-size DMS also that were part of this Go Time project that were located down in Cape Cod. So 3 full-size amber DMS. One of those was on the slide that you saw previously with the stay alert message. That was one of those arterial DMS, fully solar powered, the full-size DMS with 15 days of autonomy built in. This system just got completed and just went live, and right now it is the largest single travel time system for any state in the U.S. This shows the solar way station. We also just completed a project in New Hampshire where we did, this is our blank out sign technology, a little bit different than our dynamic message sign technology. Open closed blank out signs that are capable of displaying the status of these way stations. This was also done with a complete solar power system to operate each one of these blank out signs. So that wraps up pretty much my presentation here. You can visit sesamerica.com. We have product specifications, data sheets, some other resources that you can download. There will also be this webinar posted online within a matter of just a couple of days. You'll be able to go to sesamerica.com to be able to access that and some of the other information that we have here regarding solar and how these solar systems are designed, as well as any of our other products, whether it be our mobility line or traditional DMS or some of our retrofit upgrades. So at this point, if anybody has any other questions, I'm gonna keep everyone on mute because I think it'll be easier just to go ahead and take questions that people want to type in. But if anybody has any other questions, please feel free to type those out to me here, and I'll give a few minutes to see if we got any other questions. Okay, I haven't seen any questions here yet. We're nearing 2 o'clock. I want to stay on time with trying to do this in an hour. So thank you guys all for coming on here. Actually, I just got one question here that I'll quickly answer. And if anybody has any other questions here, by the time that we log out, please, my email address is here. You can send those to me at any time. I did just get a question on suggestions about how to discourage theft of the panels or the batteries. And that is a question that's come up quite a few times. For the MassDOT project that we did, one of the ways that they deterred theft on the PV panels themselves was to put them on a 30-foot pole. So these panels are 30 feet up in the air and very difficult to access. The batteries themselves, the cabinet is locked. It has a couple of different locking systems that it has, and so far we haven't had any issues. So by providing a battery cabinet that you can lock and putting the PV panels up on a pole so that they're not easily accessible from the ground are some ways that you can deter theft of the panels or the batteries. Another question that I have here is MPPT controller is best. Yes, definitely as any part of these solar power systems, you definitely want to have an MPPT charge controller. Not only is it going to optimize the power that you're able to draw from the PV panels and really condition it, having a MPPT charge controller that can regulate low voltage and high voltage situations is something that's going to be critical to your system. It can also monitor the depth of discharge, like I mentioned before. And the MPPT charge controllers are really meant to work in conjunction with those bypass diodes on the PV panel arrays to be able to help with current flow and keep the current from working its way down to that cell that might be shaded or multiple cells that are shaded so that those cells don't burn out. It works in conjunction with those bypass diodes to actually also pull as much available power from the PV panels, even when it has to bypass 2 columns of cells like I showed in the illustration before. So the MPPT charge controller is definitely the best charge controller that you can use. Okay, I don't see any other questions. Thank you guys all again. Any questions, please just email those out to me. And thank you guys all very much for attending the webinar today.